specifically on what needs to happen for SSE MMX. I might even start doing some of that, or preparation for I haven't thought about what needs to be done, or preparation for. So first, let's talk about what we already have. Maybe I should talk about what assembly language is. So right now, you can say a global symbol, and I think I have to say address. So we have assembly blocks that are outside of functions, and you can also have okay, so you can say okay, so what are we doing here? We are so let's unassemble so it put an assembly push FD. Let's push FD CLI. Then there's the loop, and then there's a pop FD. That's flags, by the way. Flags double. It's actually 8. No, actually, flags are 32 bits, aren't they not? Anyway, so we can have assembly there, and then finally you can put. So if you have instructions, it doesn't like the redefinition of here. Oh, we don't want to return also. Okay, so it printed hello world twice. So you can have assembly blocks on their own. You can have assembly blocks inside of functions, and you can have instructions, opcodes. If it starts with an opcode, it's a assembly instruction. So furthermore, we can say go to, let's see if this works. Go to go to my spot. I don't know if this is going to work. I don't think it's going to work. It worked. It went. So no, it printed hello world twice. Wait. Yeah, it did not work. Let's see what it unassembled as. Jump to D. There's no go to in there, is there? Let's see what happens if we do this. I wonder why it didn't give an error. Oh, there we go. There, it worked. Hello world. Okay. So look at that. We defined a go-to, and let's put a let's get rid of this. Uh-oh, bad. Oh, of course I screwed up. So it printed hello 10 times. Okay. So we have okay. So let's go look at the assembler. So first, the compiler, when it parses a statement, if it finds an ASM block, if we're inside of a function, calls compile join. If we're outside of a function, there's two cases: if it's ahead of time or if it's just in time. Fix up just in time. Otherwise, parse ASM block. Or then finally, if it gets an opcode, then it assembles one function, one instruction. Let's see. If it finds if it finds an opcode or a assembler directive, it calls comp join. Okay, so that's for each. Well, no. Anyway, so in the assembler, we get an ASM block, it continues until it gets to the close brace. If it's a start brace, it skips the start brace. If you can list assembly, it's a little bit broken. Let me show you what I'm talking about. If you say list, do you see how it generated this listing? So it has to, it's a little bit, it lags. It does the previous instruction. It prints the bytes, and it does a put line. I think that the Lex displays the characters on the line. So it prints the anyway, so we have import module org align. These are directives. Now in standard x86 assembly, you have db, dw, dd. We have, do you know what I'm talking about? In standard assembly, you say define byte and then message or something like that. Well, in my assembly, you say du8 and then you say hello. So I'm quitting. So for example, we can say du8 woohoo. I think we say 13, 10, I think we say 10. So move, oh, this is bad. What do I say? Put S? No, that's not what I say. I don't remember what I say. Okay, so where are these functions defined? They're not documented. In the kernel, I think it's kernel utils. No, it's not. Where is it? What? Find direct. String A. Okay. Put string, I should remember. Okay, put string, RSI is the input. Put string. Technically, we need to push. You have to preserve RSI. Ooh, okay. So it worked. So we defined bytes, and anyway. So where were we? We were talking about so do you want to look at how these work? These, when we're parsing, we have a compiler control structure, and it's telling it either 1, 2, 4, or 8. So the trick here is if you have something that's not defined. So in assembly, you can have a forward reference. In assembly, is this going to work? This is not going to work, is it? Yeah, it does work. Okay, in assembly, you can have a forward reference. In C, you don't really have that. So what that means is my assembler has an undefined. It keeps a list of undefined symbols, and it updates them at the end of the. It makes a list of all the spots that have undefined symbols. So what are we doing here? If it has, now it's using the C expression evaluator, and it's making code. Here's this is really mind-boggling. If I say, let's see what this does. Message +1. Now let's unassemble. Oops. Okay, so after it assembles, there's the 10, and then look here, it I don't know if this worked. I think it did. No, it probably didn't work. No, that's a relative, wait. $10.0, and then 80 A4. I don't know what that is. Okay, well, long story short, what my assembler does, how about 9 + 1? Okay, so there's a 10. So I sort of cheat, since we're already using the C compiler, and the C compiler can work just in time. We compile an expression, a C expression, and if it doesn't have any unresolved symbols, then we call an evaluation. Now, if it has an unresolved symbol, the way this works is well, there's a you see the machine code. Okay, I think it, I don't know if it's going to call it later. Okay. In the compiler, there's ASM resolve. This is where it resolves local and global symbols. There's unresolved add, unresolved globals, globals resolve, locals resolve. So what does it do? It goes through the list of all unresolved, and then it's going to patch. It's going to call this resolve. So this resolves the symbol. What does it do? If it's still unresolved, it turns it into an import or an export. Import, obviously. Otherwise, if it's there's where it does a call. So it actually executes code. So the code had some pointers. Here's the deal. When we have a symbol, it said, let's see how to explain this. So in the expression evaluator, if it has a if it's a new symbol that has not been resolved, it puts an indirection into the so the compiler makes some code to execute, and there's an indirection for the symbol, and when we do that final call off after it's been defined, then let me see how to explain this. So let's say message plus 1. How about this? Is this going to work? This is the ultimate. You look at that. Okay. So here's what it did. It had this expression, and it's going to turn that into code. What's that going to look like? That's going to look like a 32. It's going to look like an indirection of a 32-bit value plus a 1 integer. Okay, and what's going to happen? So in other words, we're going to say something like move move RAX address message move RAX add 1 or increment RAX return. So what it's gonna do is it's gonna make some code, and then later what happens is, as it's assembling, it hits this message, and what that message does is it fills in this with an address, and then finally, when it's all done with this, it calls resolve globals, and the resolve globals executes this code to it calls machine code to execute it, and if it's undefined, then we make an import or export. If it's RIP relative, then we have to subtract. If not, import not immediate not relative. So it has to know if it's a relative or an absolute value, and then finally it stores the value into the code at the spot where. So so it has to keep track of the address of this instruction, and when it's doing the resolving, it stores it into the code. Anyway, so the let's see if this works. I don't think this works. Define byte message, not define byte, define U32. It did work. So it stored a 3FD7. Now let's look for a message. This is not exported. Let's export it. Okay, now it's going to be exported. So message is 3FD72E7F. 3FD72E7F. So how did this happen? We're doing a define byte, define word, and it parses an exception, and it makes a undefined global ref. There's a linked list of undefined globals, and you can have a dupe what if we say, how does this work? 10 dupe message. Does that work like that? I don't even remember my syntax. I have to go double. I don't do assembly. Well, I do it, well, not every day. Okay, why did not that work? Oh, well, maybe I did better than I thought. Now that would screw up the, it's a good thing it didn't work. You want to know why? Undefined symbol. Huh. Okay, so let's say 13. Now we have a bunch of 13s. So yeah, I would not have correctly handled that because it only makes one patch for each symbol. Anyway, so parse define. Now you might want. Now the main thing you have to do is parse instructions. Am I right? So what do we do for parsing instruction? So it parses the. It gets the opcode. It lexes past the opcode. It gets a. There's a. There's a structure for opcodes. And it has a variable length list of addressing modes. So when you when the assembler is initialized during boot, when the compiler is initialized, it's going to make one entry for each of the addressing modes. And there it's figuring out how many arguments. Each opcode has to have a fixed number of arguments. What that means is so I made my own opcodes. ROL with 2 arguments is one opcode, and ROL with 1 argument is a different opcode. So I don't allow different. If you have different number of arguments, you have to use a different opcode. So this is, if there's an argument, then it parses an argument. If there's 2 arguments, then it parses 2 arguments. And when it parses an argument, it stores it into a structure. So parse argument. So what do we have? To parse an instruction, we have identified we know the opcode structure. We have parsed the 2 arguments. Oh, it's either relative. It could be a relative or an absolute. It could be a relative or an absolute. So we have parsed the 2 arguments, and once you've parsed the 2 arguments, you parse the instruction. So there's parse argument and parse instruction. Now let's go look at So to parse an argument, you if there's an identifier, it checks if it's a register. If it's a register, it the register has been set to none. But if it is a register, then it changes the. It sets the register number, sets a register type, and other stuff here. If it's a class or an internal type, what we're doing here is now I don't have extreme flexibility. So what if you say move RAX something like this. Okay, so what we have here is we have a class, a C task class. So it's an offset. I think, why are we not doing an expression? I thought we did an expression. Now if it's a class or an internal type or a keyword, oh, okay. What it's doing right here is when it's parsing the argument, you might want to say it's an I8. It didn't like that. It didn't like that. I think we have to say you. No, we don't have to say in. So the error messages are off by 1, by the way. Oh, we're loading into RAX, so it has to be a 64. So how does it know that? Well, so we can set the size, otherwise the size is undefined. And so this is how you parse an argument. So you, I think you can parse a, there's an immediate value, parse immediate. If oh, now I know what's happening. I think these keywords are internal types. Is that correct? I think so. Why do I do class? Anyway, so this, I was wrong. This is not for classes. This is, I think this is only for these keywords. Now what about an integer that it finds? So if it finds an indirection, it should invoke the compiler, the just-in-time compiler, parse immediate. I guess that's what it is an immediate. Anything that's any number is called an immediate, I guess. Even if it's what about an offset? Parse immediate. Parse immediate. What does this do? Here's where it calls the it invokes the just-in-time compiler, and it's going to do a call, isn't it? Isn't it going to do a call? Yeah, there's where it does the. If everything's defined, then it does a call, and so at this point, the argument can have a couple registers. Sometimes you have 2 registers, It can have a segment register. Sometimes you override the segment. It can have a scale factor, and it can have an immediate, and it might be relative or absolute. So now what do? You have to find out which format of the instruction to use, based on, because it can have multiple. So store number, that's not what we're doing. Parse instruction. So we make a mask of so these are the addressing modes. Some of them have to be a certain register, and what we do is we make a 64-bit mask for all these different addressing modes, and then what we do is we by process of elimination, we eliminate different modes using the mask. So if the size is 64, then that means all we have left are the 64. If the size is 64, maybe the mask results in these three. And then what we do is we compile each of these three and we keep the shortest. Okay? So we assemble each of the three and we keep the shortest. So where are we doing that? So after we have limited to the, we've made the mask, limiting which one, and then we do a test. We go through all the different formats of the instruction, and we do a test if the mask has not been set to 0, then this sub addressing mode might be correct. And then what do? We assemble the instruction because it might work, and then finally at the end, after we've assembled it, when we check if it's better than the best. Okay, so we have to assemble the instruction, and then at the very end, we check if it's better than the best, and then if the best is non-zero, then we store the opcode prefix, we store the address size, we store the modder and the SIB. This is for if you. Now here's something interesting. Okay, so you can have prefixes, opcode, modder, SIB, displacement, immediate. So this is the format of an instruction. You don't have all of these all the time. What I did, which was genius, is I don't really need 16-bit code. It's not very important. Now this table is just for 16-bit, but here's a trick. There's another table for 32-bit, and what I did is if you use a prefix, you can force it to use the 32-bit table even if you're in 16-bit mode. And so to make a long story short, I didn't have to make my assembler do 16-bit. I always do the 32-bit version. So what does that mean? It means the instructions are longer than they should be, and but you know what? You don't need to be doing 16-bit assembly. There is no reason for you. The only place you need 16-bit assembly is in the you need it in the bootloader. You need 16-bit assembly. There's the U16. And then finally in the kernel, the bootloader calls the kernel, well, it's in 16-bit mode. My bootloader calls my kernel in real mode. And then in my kernel, calls a couple BIOS routines in 16-bit. Then it changes to 32-bit and then to 64-bit. And so there's one other place you need 16-bit assembly, and that's in the multi-core. When you start up the other cores, they start in real mode, and you have to convert them to long. You have to get them into long mode. So so to make a long story short, how would we go about adding MMX SSE? So I have the registers, so it will identify them. We need to add all the MMX SSE. We need to add all those instructions, all those opcodes we have to add to the table. So that means somebody has to I think that they start with P a lot of times. All the P, CMP, P, all those P instructions. So we need to add to my opcode file. We need to say PMINUD, and then we need a syntax for so how's this going to look? So in this opcode file, we're going to say something like opcode PMINUD. Then we're going to give 0x66 0xof 0x38, then a comma, and then this is where it gets tricky. One of these is a /R. Is that a is this two opcode? What the hell is this? Is this two instructions? I can't tell what they're doing. What the hell is this? This is two instructions? Well, whatever it is, there's a format for the /R. And what that does is, that's, well, it's, you see these instructions have the /R, and that what that means is whatever register, whatever XMM register they used, the register number gets stored in the opcode, something like that. Well, anyway, so you have to take. So let's say it's register number 5. Then you add 5 to what do you add it to? I guess you add it to I don't know. You would add 5 to this 3B, or maybe you add it to the modder or something. I haven't really looked at these, to be quite honest. The /R definitely means you add the register to, there's a modder table. Oh, it will tell us, won't it? If we, let's go look at the format of instruction format. So the modder has the register. You see how anyway, well, it's a no-brainer that no, the /R goes into the opcode, not the modder. Some instructions like push so if it has a /R, perhaps you put it there in the modder. No. The push instructions are those push /R? Let's look for push, see if that's /R. Push is +R. Okay. Well, where does it define? I forgot where it tells you. You might have to get another book or another web page. You might have to look this up on the net. Immediate. So this tells about the modder. Oh, here we go. So the /R indicates that the modder byte of the instruction contains a register operand. Okay. What about the XM? What about the XM11? The +R +W. Relative. Here we're getting warmer. We're getting warmer. We're boiling hot. Here we go. So this tells how to do it. Where's the /R? Anyway, when I wrote my assembler, I could cheat and look at how it assembled with another assembler, but I don't have another assembler today. That was when I had Turbo Assembler, and I could cheat and see what it did and then do the same thing. So it was a lot easier. So what I would do is get another assembler and see how it codes these, and then it should be really obvious how it's supposed to work. Okay. So once you add opcode entries, you might need you're gonna need to put the it's going to need a mode for what is this called? arg. So this is the argument type mode. So I already set some modes for MM64, so I already have the modes. So you're going to put something like XS, and then once you have the modes, then in the you need to modify the argument mask in order to whittle down to the right mode. So if it's a 128 size, then you're gonna clear some bits. If it's and then finally you're gonna have to parse the instruction with you're gonna have to code the machine code for that instruction. This is for example, here's where it's encoding relative 8 branches. It's setting the rex. Well, that's if it's 64, but it's setting the rex. It's copying the immediate value into just look at this and do it. I guess I have to. So here it has a modder. You're going to need something for the cur. What is cur? Cur is a ASM instruction. So you're going to need something here in order to. This is the machine code representation of the the MMX or the SSE. You're gonna add a byte or a couple bytes, and then you're gonna, after you've identified the mask, you're gonna after you've done the mask, then you're going to this is handling different modes. This is RM8, so this is a big if, and so if it's not RM8, it's relative. There's only a couple options, I guess. If it's got 2 arguments, you do. So you're going to add an if. It's going to be something like else if arg type x. You're going to do something very similar to this. And then you're going to do something like cur.xmm equals, and then you're going to put the register number. It's going to be one of these TempleOS reg. Perhaps something like shifted over 3, some crazy number here, plus some other register. TempleOS2. It's going to be something like that. And then down at the bottom, you're going to put if here it's storing the modder and stuff like that, storing the immediate. Then you're going to put something like if has XMM store code best XMM, something like that. And then up here at the where it's doing the arg mask, you're going to say if you're going to say if register type equals, you should put these in order of most. If you did a statistical analysis of which opcodes were most frequent, that would tell you which should go in front. Although I think it goes all the way through this routine. You want to make it efficient. And so in this case, you're going to say result equals 1 argt xmm. So you're gonna make the mask if result type equals if register type equals xmm, then you're gonna set the mask for that, and there, you're done. Anyway,